It is great to have Ben Van Rooij here today. Ben has dedicated his whole career to reinforcement learning, starting when it was not hot at all, has explored it, has looked at applications in finance, in inventory management, and is very well known for a lot of fundamental work. More recently, work related to Thompson sampling. And as you know, in reinforcement learning, the problem is to control an agent that is learning from the environment. And one of the crucial questions is the balance between exploration and exploitation. And I would say that Ben is one of the really world authorities on that subject. He's well recognized as fellow of IEEE and NFORMS. And it is quite impressive to see where his former students are. You name it, the top universities, MIT, Stanford, Columbia, and so on. And he's placing students also at good research labs. This is the yearly Optimization and Statistical Learning Distinguished Lecture. We only have one distinguished lecture a year. We started last year. The first speaker was Leon Botou. And now we're very happy to have Ben Van Rooij. And Ben, please take it bit by bit.
Thank you very much. And Georgia, thanks for inviting me. It's really a pleasure to be here with all of you. This is a talk on the role of information, or some thinking we've done on the role of information in reinforcement learning. And it's work done with these collaborators of mine at DeepMind. Okay, here we go. All right, so this statement has been attributed to Harry Clough, who is an Air Force researcher, though it might not be entirely accurate. It's somewhat accurate in sentiment. The statement may sound vacuous, since minimization, as you operations researchers know, can be converted to maximization via negation of an objective. However, some reflection reveals a deeper observation in this. The subjects of supervised and unsupervised learning aim to mimic observed patterns, minimizing differences between model and data. Reinforcement learning, on the other hand, takes an open-ended view. A reinforcement learning agent learns to improve its behavior over time without a prescription for what the behavior ought to be or the limits of performance. If the objective takes non-negative values, minimization suggests a well-defined desired outcome, whereas maximization conjures the pursuit of the unknown and unbounded. Okay, so in reinforcement learning, distinctive element is that the nature.
Ben, sorry, I'm going to interrupt you for a moment. I just want to tell everybody who's present that this lecture is being recorded. It has to be done. Please go ahead.
Okay, a distinctive element of reinforcement learning is that the data depends on the agent's behavior. And this bears important implications on the need for data efficiency. So in supervised and unsupervised learning, data is typically viewed as static or possibly evolving, but very slowly. If the data is abundant, if there's a lot of data, as is the case in many modern application areas, the performance bottleneck in supervised learning often lies in model capacity and computational infrastructure. Okay, so if you take an example of a success story in supervised learning like GPT-3, which learns to generate documents. It uses a neural network with about 170 billion free parameters trained over around 6 months with essentially all the documents in the world. Okay, and it can write human readable documents as a consequence of that. So it's all about capacity, number of free parameters, and the intensive computation that goes on in the training. Okay, the data distribution is stationary, so you just want to mimic what you've seen in the data. Okay, now in reinforcement learning, most success stories of reinforcement learning to date are in simulated environments. Right? And of course, when a reinforcement learning agent operates in a simulated environment, the data distribution evolves with the agent's behavior. But because we're simulating, you can generate enormous amounts of data, vast amounts of data. And because of that, data efficiency isn't as big an issue as it might be, and computation still remains a bottleneck. Okay, so you throw more compute at this, you do better. Right? Just simulate more on a grid of computers. Okay, now if we want to transition over to reinforcement learning in real environments, you have to be prepared to deal with quickly evolving data, because you want to use data efficiently, right? You want to quickly learn as much as you can from the data, be able to change the agent's behavior quickly, and then deal with the quickly evolving data distribution that results from that. Okay, so this is like a new game. You have to really worry about data efficiency. Now, when you look at, so this is a cartoonish plot produced by a leading roboticist who's tried applying various state-of-the-art reinforcement learning agents to simple robotics tasks. And this is meant to represent his takeaway from how these agents perform in the simplest of tasks, where you want to control a robot arm to stack a few blocks. Okay, and what he found is, if you learn in real time with the robot experimenting with blocks to stack blocks, it requires weeks of training before the robot does anything that looks non-random, and years of training for it to achieve any level of performance that we deem as competent. Okay, so clearly that is not the dream of reinforcement learning, to take years to train a robotic arm so that it can stack a few blocks. Okay, but if you do this in simulation, no problem, right? In a simulated environment that's simulating the physics of this, you can simulate all you want. You can simulate 1,000 years and a robot can stack blocks, no problem. All right, and it's easy to cook up problems where existing state-of-the-art reinforcement learning agents behave very inefficiently, right? And here's an example, such a simple example. This is a problem where an agent can push the cart left or right over each time step, and the agent receives positive feedback if and when the cart is almost perfectly centered and almost perfect, and the pole is almost perfectly balanced. Okay, and this is a demo of a DQN agent. This is a popular agent in reinforcement learning, a simple one that people like to study, but you'll pretty much get the same results using any state-of-the-art reinforcement learning agent, with DQN, after about an hour of training, you get something that looks like this. After about 5 hours, this, and after 10 hours, the robots decided that it's not really ever getting any reward. Oh, and I should mention there's a small cost to expending energy here. So the best thing to do is really to do nothing. Okay. On the other hand, there's a simple fix you can apply to generalize DQN. And with this simple fix, after an hour training, at least you're doing something. After 5 hours, you're starting to see some intelligent behavior. And after 10 hours, it's learned to perform the task almost perfectly. Okay, so the idea here is these state-of-the-art agents, it's easy to break them by coming up with examples where they're incredibly data inefficient. And there's often fixes that allow agents to deal with these examples. But what we want to do is come up with a holistic way of thinking about this so that we handle all the examples at once. And what I'll talk about today motivates this kinds of fixes that would fix the performance of this agent in this environment. But hopefully we're working towards a broader theory that will allow us to more generally design agents to be data efficient. All right, so what drives data efficiency in reinforcement learning? So there's what information the agent is designed to uncover, what knowledge the agent retains from the information it uncovers, and how it goes about acquiring that information. Those are really the key issues that drive data efficiency. Okay, okay, just to review, the way reinforcement learning agent works is at each time t, the agent applies an action at to an unknown environment, and the environment spits back a observation ot plus 1. And so the reinforcement learning process is just this sequence of actions and observations. All right, so here's an outline for today. I'm going to start with some inspiration from another field, and then I'll talk about, I'll give you some background on reinforcement learning agents. Then I'll talk about some design principles that we've been thinking about. And then cost-benefit analysis one might do to think about how you want to make design decisions in a reinforcement learning agent. And then I'll talk about implementation and computation approaches that may make all this a reality. All right, so let's start with some inspiration. So data efficiency is not a new topic, and it's useful to draw some inspiration from another field that's grappled with data efficiency issues. And we'll talk a bit about communication here as a source of inspiration. In a communication, the goal is typically to transmit data through a channel in a way that maximizes throughput measured in bits per second. In reinforcement learning, an agent interacts with an unknown environment with an aim of maximizing reward. An important difference that emerges is that bits of information serve as a means to maximizing reward, not an end. As such, an important factor arising in reinforcement learning concerns weighing of costs and benefits associated with acquiring bits of information. Okay, so So the real new thing in reinforcement learning at some level is this notion of cost per bit that arises to some extent when you do lossy communication. But this is really pronounced in reinforcement learning and a major issue to consider beyond what is typically the focus of communication. Nevertheless, some concepts from communication can guide our thinking about information and reinforcement learning, as hopefully we'll see today. All right, so communication was an active area of research at the turn of the 20th century, with an emphasis on scaling up power generation to enable transmission of analog signals over increasing distances. That's a picture of Marconi, who won a Nobel Prize in physics for developing approaches to scaling up power generation so that he could transmit signals over longer distances. But back then, encoding and decoding of signals was handled heuristically. And there's this feeling that it's all about power generation, generate more power so you can send the signal farther. So in the 1940s, communication took a turn with Shannon's maxim of information first, then computation guiding subsequent developments. Shannon really shifted the focus to understanding what's possible or impossible rather than just scaling up power. And this initiative introduced the bit as a unit of information and established fundamental limits of communication. His maxim encouraged understanding what's possible and deferring thinking on how to compute things. Okay, and this led to the design of decoding and encoding and decoding algorithms that attained fundamental limits in the 1960s. And finally, around the 1990s, we really got good practical implementations of these things. And it's fair to say that made the world a different place. Yeah. Now, it's interesting to reflect on the development of reinforcement learning and how it compares. There's been a number of people driving the development of reinforcement learning, but probably someone who's really in a constant force pushing this area is Rich Sutton here. And Rich is a friend of mine, has always had this posture, which I frame as a maxim of computation first, then information. Right? Rich thinks, don't worry about data efficiency. There's going to be so much data in the future that that's not going to be an issue. Let's just worry about how to compute things so that given enough data, we'll get a good solution. And he really drove the development of heuristic approaches to RL in the 1990s. And then his doctoral student, Dave Silver, in the past decade or so, really pushed hard to scale up how these ideas are used and how much computation you can throw at these ideas to accomplish great feats using these sorts of algorithms. Okay, so the question is, how do we, and all these feats are in the domains with simulated environments. And so the question is, how do we get from here to a point where reinforcement learning can meet its ambition of being used in real time in the real world to learn to do useful things for society? Okay, and perhaps it's time to revisit, maybe reverse this maxim, and think about how to carefully quantify and optimize information in reinforcement learning. All right, so let me give some background now on reinforcement learning agents. For those familiar with reinforcement learning, this should be a review. But in reinforcement learning, we have this agent environment interface. At each time step, the agent takes an action and the environment emits an observation. And at any time, there's a history of interaction, action, observation, etc. And one way to think about the environment is you can formalize it as a triple AOP, where there's an action set. This is a set of actions that the agent chooses from. There's an observation set. This is a set of observations that the agent can register from the environment. And rho characterizes observation probabilities. And so rho tells us what the probability of the next observation is conditioned on the history and the current action. Okay. Now in reinforcement learning, you assume that the interface with the environment, which is a set of actions and a set of observations, is known to the agent. But typically the observation probabilities are not known, and learning goes on because you don't know those. Okay, so here's an example. Consider a dialogue system. You could imagine a sequence of interaction. The agent says, how can I help? The environment spits back a message. How do I replace a bulb? And this conversation can continue, right? And so reinforcement learning should supply technologies to develop this agent so that it can learn over time to interact through such an interface in a way that generates value. All right, so as I mentioned, uncertainty plays a big role. I mean, without uncertainty, there wouldn't be learning. And how do we think about uncertainty? So here's where, what I'm presenting starts deviating from the common reinforcement learning literature, in that I'm going to try to carefully think about uncertainty and information. Okay, so there's really three sources of uncertainty in reinforcement learning. There's algorithmic uncertainty that has to do with randomness in how the agent's going to choose the next action based on the history. There's aleatoric uncertainty that has to do with, if you condition an environment, given a known environment, how is the next observation generated condition on history and action. Okay, it's aleatoric uncertainty. And then there's epistemic uncertainty, which is uncertainty in the environment. So the agent doesn't know what the environment is. You can think about that in terms of probabilities. And epistemic uncertainty is that representation where there's a probability assigned to each environment, and those probabilities adapt to history. Right? That's epistemic uncertainty. History tells you about the environment, so that allows your distribution to concentrate over time. Mm-hmm. Okay, so learning is really about epistemic uncertainty, and learning is about reducing epistemic uncertainty. And in quantifying uncertainty and quantifying what's being learned, information theory offers useful tools. So these, when I talk to information theorists about this, they say, why are you even using this? information theory was really designed to think about communication, and you should develop custom tools for thinking about information and reinforcement learning. And I've tried, but actually so far I haven't been able to do better than what's supplied by information theory. So sort of an interesting connection here. All right, so here's my information theory cheat sheet. Since I'm relatively new to information theory, I need one of these. So if you ask a question like how many bits are required to identify the environment, information theory quantifies that in terms of entropy and writes it in this way. It's entropy of the environment is how many bits you need to acquire in order to identify the environment. If you ask how many are still required after you observe a certain history, well, that's a conditional entropy. Okay, conditional entropy of the environment, conditional history. And then you can say, gosh, well, given that, what should I call the amount by which entropy reduces in each time step? The amount I learn, the number of bits I learn in each time step. And that's the mutual information. So here we have the mutual information between the environment and the action observation pair conditioned on the history. Okay, that's how many bits you learn in a time step. Okay, so policies and rewards play an important role in reinforcement learning. Okay, what's a policy? A policy just is a mapping that attributes a probability to each possible action conditioned on history. Okay, so policy maps history to action probabilities. A reward function maps history to reward. And using these, you can define a value for a policy. So this value, V bar pi, is the expected reward over a horizon capital T condition on the environment and the policy you're using. Okay, it's interesting to note that this expectation is really an integral over algorithmic and aleatoric uncertainty. Right? We're not integrating over epistemic uncertainty here because we're conditioning on the environment. Okay. You can also define an optimal value, V bar star, which is just a supremum over policies of V bar pi. All right, so let's talk about notion of agent policy. Now, policy is a mapping from history to action probabilities. An agent policy is just a policy that the agent is using to select its actions. Okay, so pi agent is what the agent is using. Okay, so each action AT is sampled from pi agent condition on history. Now, given a particular policy, you can talk about regret. Sort of an interesting object. It's the I'm going to define it as the expected difference between the optimal value V bar star and the value that's generated by a policy pi. Okay, over a capital T time steps, over the horizon capital T. And this expectation is with respect to epistemic uncertainty, right? Because the way V bar pi and V bar star were defined already integrated over aleatoric and algorithmic uncertainty. So this expectation here is an integral over epistemic uncertainty. Okay, and so regret tells you how far short you're falling from optimal behavior. Okay, so one possibility is to design pi agent, the agent's policy, to minimize regret. Okay, that seems like a reasonable objective, but it's very hard to do. You can't really put this in an optimizer. It's too complicated a problem, and even as a principle to guide agent design. It's not clear how to proceed. Okay, so so we really need a simpler objective to work with if we want practical guidance for agent design. And today I'm going to talk about one approach to that. Okay, before going further though, to make things a bit more concrete, let me go through DQN, which is a simple and popular agent. And this will serve as like our prototypical example of what an agent might be, okay? And I'm not going to go through all the details, but I'll go through enough so that you can sort of see how such an agent works, roughly, and how the ideas that we'll discuss might factor into this. All right, so DQN was designed for an arcade game interface. So the idea is it's designed to operate with actions that are joystick maneuvers and button presses, and observations that are images captured from a video rendering. Yeah. So it's designed with that interface in mind. And you know, the first version of DQN years ago impressively attained superhuman level performance in most games. So it's one piece of software, you know, without any further tuning, you can plug it into any arcade game, and it usually learns to do better than a human. Okay. So how does it work? Well, DQN, you know, one component is a big neural network. And the neural network takes as input a series of recent frames. I think it takes 8 frames. The original version took 8 frames as input, but you could generalize that. Okay. And it outputs action values. So this Q theta T, the idea is theta T is the neural network weights. And the output of this neural network, you know, given the input ST, the output is Q theta T ST comma action. And the idea is that you could, for any action, this assigns a score to how desirable that action is. Okay, and the idea is that that score can guide decision making. Right, the agent could say, I want to pick the action with the best score. Okay, but what's being learned over time as data is observed is the weights of this neural network, the theta T. Okay, another component. Oh, and you know, given these scores, you could choose an action guided by them. And the way DQN chooses actions is through an epsilon greedy approach, where at each time step, DQN chooses the action with the highest score with probability 1 minus epsilon. And with probability epsilon, it chooses an action uniformly at random from across all possibilities. And then another component of DQN is called the replay buffer. What the replay buffer is a cache that stores many recent observations. Okay, so there are these frames coming in from the video capture. Oh, and also actions coming in from, you know, what the agent selected. And a replay buffer stores a lot of that, right? So you can replay what happened, you know, what were the frames and what was the action, right? That's a replay buffer. Now, you know, because there's so much data, right? DQN simulates for a long time in order to generate a good performing arcade game player, because there's so much data generated in the process, and memory is finite and compute is finite. The replay buffer also has to eject data in a way that respects memory constraints. Okay, so it doesn't keep all historical data, right? It gets rid of all data over time and is restricted to a finite size cache. Okay. And as time progresses, there's constant training going on where the neural network is constantly ingesting data from the replay buffer and doing stochastic gradient updates using a temporal difference step. It's like temporal difference learning going on constantly, updating weights using data from the replay buffer. All right. Maybe, I know you didn't want to encourage conversation during the talk, but let me pause it for 1 minute in case there are questions.
So the data that is ejected is temporal only? The decision is only temporal?
Okay, so there's, I should be, to be fair, there's many versions of DQN, right? And so the original version kept 1 out of n data points and threw away the others, and then would also get rid of the oldest of the samples it kept. Right? That's roughly how the original version worked. But if you do a search on replay buffers, there's probably, 100 different approaches people have tried by now. Okay, let me talk now a bit about design principles that can be used to guide designing a better agent. Okay, and there's a few concepts that I think are important in thinking through design principles for informationally efficient agents. 2 are driven by the fact that, driven by boundedness. And these 2 concepts, which I'll talk about in more depth in the next slides, are agent state, which is something that is recorded to inform the agent about its current situation in the environment, and epistemic state, which is something recorded to inform the agent and inform the agent's beliefs about what the environment is. Okay, and one sort of mathematical way to think about the distinction here is, agent state is more of an ergodic kind of thing, and and epistemic state is something that's transient, because, as you learn, your knowledge tends to increase in a unidirectional way. Another pair of concepts is driven by the need for prioritization. The idea is, for a bounded agent, the agent state can only maintain limited information about history, and the epistemic state can only maintain limited information about history. So you need to prioritize what information goes in there. And there's 2 concepts I use to guide this. One is called an environment proxy, and that tells you what you would like to retain in terms of knowledge about the environment. And then there's a notion of a learning target, and that's for prioritizing what you want to learn about the environment. Okay, so what you want to acquire, what information you want to acquire is a learning target, and what information you want to retain is the environment proxy. Okay, and the distinction here is really, how you want to summarize what you know about the environment, and how you want to think about what to gather. Okay, so agent state. The idea here is that a bounded agent can't possibly evaluate an arbitrary function of history, right? The reward function can't depend on all history, because then, if that's the case, the agent can't even know how well, can't even assess whether it likes what it's doing or not. And the agent can't use policies that depend on all of history, right? So the agent state is a useful construct, and the idea is it should be something that is incrementally updated where state at time t+1 just depends on the current state, the action, and the observation. Okay, and you want your reward function to be designed so that reward is a function of agent state, action, and observation, and not the entire history. And it's useful to consider policies that make decisions just based on agent state and not the entire history. Okay. But in DQN, what's the agent state? Well, in the DQN agent state is a series of 8 recent frames from the video feed. Okay, that's the agent state. Right? And that's incrementally updatable, right? When you take in a new frame, just drop the least recent one. And so you can incrementally update based on the new observation. Okay, epistemic state. So any agent needs an epistemic state. That's its representation of what it knows about the environment. Okay, a bounded agent needs an incrementally updated epistemic state. So we'll call the epistemic state PT, and PT plus 1 is a function of PT, the agent state, the action, the observation, and maybe some algorithmic noise. Okay. And what's the epistemic state in DQN? Well, the epistemic state is the neural network and replay buffer. Okay, these guys are the representation of what the agent is currently retaining in terms of knowledge about the environment. Okay, now in some sense, an ideal epistemic state would be the entire history. But part of the point here is you don't want to have an unbounded object that you have to maintain. Right? History is growing over time. And also you don't want to have to access so much data all the time, right? You want a compressed representation that encapsulates sufficient knowledge for the agent to use to behave intelligently. Okay, so I've talked about agent state and epistemic state. Let me talk about these 2 other concepts: environment proxy and learning target. And these are concepts which really impact how we think about epistemic state. Okay, cursive knowledge. The idea with the environment proxy is that, you know, environments that we want to apply agents to are very complex, and there's too many bits to store or access for us to think of all information relevant to the environment, for us to think of putting all that in the epistemic state. Okay, so somehow the epistemic state needs to discriminate and say, I don't want to retain all information about the environment. It needs to prioritize which bits to retain. Okay, and the environment proxy is a concept that can guide that. The idea is the environment proxy psi is a set of features or statistics of the environment. And the idea is to prioritize retention of bits that tell us something about the proxy. Okay, so if there's a bit that tells us about the environment, but is irrelevant to the proxy, just throw it out. We don't want to keep it because we have to prioritize. Okay, so that is the proxy concept. Okay, so in DQN, what's the proxy? Well, the proxy is this neural network, which is representing a value function. And the way to think about the proxy there is it is outputting a prediction of a sum of future rewards. The proxy is outputting a prediction of a sum of future rewards given the current agent state and the current action, right? And so if you knew what the environment is, you could figure out what that prediction should be. Right? We don't know what the environment is, so we don't know what that prediction should be. But whatever the prediction would turn out to be if we knew the environment is a statistic of the environment. And we can use that to discriminate and only retain bits that are relevant to this proxy, okay? Now, I should mention as an aside that the choice of proxy is hugely important. and an area that requires a lot more thought. And that's demonstrated by this team. Oh, I meant to cite them here, but somehow that dropped off. Some folks in Canada worked on this, where they took DQN and they said, instead of just applying DQN to learn a prediction of future rewards, let's try to get DQN to learn many different things. Okay, so let's calibrate the neural network. Let's have a neural network with many outputs, and let's calibrate those outputs using temporal difference learning to predict many different things, not just reward. Okay, and they did that in the context of Miss Pac-Man, where the neural network predicts many things that were related to reward but aren't reward. And by doing that, they reduce the amount of data required to play Miss Pac-Man at a top-notch level by a factor of 1,000. Okay, so proxy design can have a major impact on information efficiency.
Uh-huh.
Okay, so learning target. Learning target also is an important concept, and it's separate from the proxy. And this addresses what I call the curse of curiosity. And the idea is that if you want to gather all information that's relevant to the proxy, that may actually take a long time in itself. And so the idea is to prioritize which bits the agent should actively go after and seek. Okay, so learning target phi is a set of features or statistics of the proxy. And they're statistics that are sufficient to generate what I call a target policy, which is a policy that you would apply after you learn this target. Okay, so the idea of the learning target is to prioritize acquisition of bits about the target over other bits, and not just try to gain all bits about the proxy, which a curious agent might do. And in DQN, it's not really clear what learning target drove the design. You could, try to be creative and think about what learning target may have motivated that, but it's not entirely clear.
Yeah.
But in some sense, our fixed version of DQN that I talked about earlier, that's able to solve this pole balancing problem quickly, you could think of that as being motivated, the fix as being motivated by clarifying a target and how to gather those bits. Okay, so I talked about a few factors that, a few concepts that represent factors one should consider in designing an agent. And to sort of put it all together and start thinking about how to make design decisions, you need some framework for cost-benefit analysis. And as I mentioned earlier, just thinking in terms of minimizing regrets, it's not clear, how to make progress with that. It's the interdependencies are pretty complex. And so this is another approach, which is to bound regret using interpretable terms, and then to have this bound as a guide for agent design. Okay, so this is a regret bound that applies for all agents and all environment distributions. Right? And there's a few terms in this bound. This is the entropy of the learning target. Okay, so this is how many bits the agent is trying to acquire. this term here is the regret of the target policy. So this is regret that we're not going to avoid. This is regret that we're going to stomach just because we're going to settle with learning the target. Okay. So if our goal is to learn the target and we learn the target and we apply the policy we get from learning the target, we're going to get that regret anyways. Okay. But the most interesting term is this term called the information ratio. And you must have heard this term since Dan Russo was your colleague for a while. But this came out of his dissertation, but has been substantially generalized since. And the information ratio is really trying to capture this connection between reinforcement learning and information theory. It's trying to quantify in some useful way this notion of the cost the agent is incurring per bit of information that it's going to retain in its epistemic state. Okay, and the information ratio is sort of a complex object because it's impacted by how the agent selects actions. And it's sort of, it's a very elegant object, it seems, and has sort of spawned a small community, mathematical community of its own, studying the information ratio and what you can do with it. And there's elegant mathematical results coming out of that area. Okay, so the idea is to design an agent or use this regret bound as a guide for agent design because the terms are more easier to interpret. And so the point here is that this bound isolates some factors we should consider in agent design, like regret of the target policy, the number of bits required to resolve uncertainty about the target, and this information ratio. And again, the information ratio captures the trade-off between immediate regret and information gain. And the design of a proxy and a target and all that can influence this. I'm not going to define exactly what I mean by information gain here because that'll bog us down. But the numerator there can be thought of as the contribution to regret of the action at time t squared. Okay, and I don't want to talk about the square because that'll bog us down too. But mathematically, somehow you need the square there. Okay, the other thing that comes out of this concept is it inspires an algorithm called information-directed sampling, which involves simply selecting your action at any time to minimize the information ratio. Okay, so the agent, one way the agent can select actions is to minimize information ratio at each time. Okay. All right, let me talk a bit about implementation and computation. Now, how can these ideas be used to, for example, create a new version of DQN that is much more data efficient, or for that matter, create a new agent that's much more data efficient? Well, an enabling technology that's been emerging, that's really useful for this is in the area of what's called Bayesian neural networks. And you can use Bayesian neural networks as a representation of epistemic state, right? So the idea is in DQN, your epistemic state is a replay buffer plus some point estimate of your proxy. With a Bayesian neural network, instead of just a point estimate, you could be representing beliefs about what the proxy might be. And that's much more powerful as an epistemic state because you're managing information much more coherently. Okay, and there's been a long literature in this area, but my collaborators have been developing the next iteration of this, and we call it epistemic neural networks. And the way you train them is also deserves some innovation, and we call that epistemic SGD. Okay, and so the way to think about what you could do with this kind of technology is, something like DQN represents its knowledge in terms of a neural network that outputs a score for each action given an agent state. Okay. An epistemic neural network, the idea here is the neural network takes an additional input, Z, which is sampled from a reference distribution. Let's just make that normal. Right? And for each Z, you output a different scoring function for the actions. Right? And the idea here is if you sample Z's from the reference distribution, it should be like sampling scoring functions from a belief distribution, perhaps a posterior distribution in the ideal world, but you could have something looser than that. We'll call it belief distribution. Okay, and so these algorithms are meant to train architectures of this variety to more coherently and comprehensively represent essential knowledge. All right, so so when you look at the real cutting edge of reinforcement learning agents, one example that comes to mind is Mu0. Mu0 is an agent that can be plugged into a very wide variety of environments, and in many cases achieves the best performance. And three notable cases is where you plug it into a chess simulator, a shogi simulator, or a Go simulator. And in each of those cases, within 4 hours of compute time, within 4 hours, but with immense compute time, computational resources, it learns enough to beat the human world champion in each of these games. Okay, so it's quite kind of impressive. One piece of software that you can, without any tuning, plug into so many different things and have it do well. Now, it's not very data efficient, right? Because it requires intensive simulation, right? I think I did a back of the envelope calculation once. In those 4 hours, if you just had one thread of simulation on a standard, computer laptop, I think it would take a few thousand years at least, or something like that. Maybe much more. Okay. But the interesting thing is when you take state-of-the-art agents of this variety, it's easy to break them. It's easy to come up with simple examples of environments where they can't perform well because of data efficiency. And that cart pull environment I showed you earlier is one such case. But the ideas I discuss are really trying to offer a framework to fixing these things. And we're currently designing, and we have been able to fix agents like Mu0 on particular environments to make them do the right thing. But right now we're trying to design a new agent that sort of from the ground up that is meant to be adhering to these principles. All right, so. I think reinforcement learning holds great promise. Been very successful with simulated systems, but data efficiency is a real bottleneck for us. And hopefully, if we can all understand the role of information in a deeper way, we can unlock the potential of reinforcement learning, perhaps even enabling artificial general intelligence. And I'll close with a demo of, some people say, gosh, reinforcement learning will never be able to do anything useful in real time. But this is this generalized DQN agent. If you have it controlling 100 workers trying to balance the cart pull system, 100 instances of that in parallel and gathering data from all of them in real time, in about 30 seconds, it learns to do a perfect job. That's it. Thank you.
Very good. Thanks a lot. We cannot do clapping, but that's great. Let's have some questions.
I have a question. So let's say if I have a bunch of data points, like collected previously, like by not so optimal agents. So is the optimal way of utilizing the data points just you know, put them into the replay buffer, or there would be like better ways, like following the information theoretic framework?
Well, I think that that actually this notion of say an epistemic neural network is very useful for that, because it'll tell you what the data informs you about and what the data is not informing you about. Right? If you just generate a point estimate given the data, you don't know that. Right? It's really essential there to understand what the data is telling you, what the data is not telling you. And so I think it's better to use a richer knowledge representation like that. Now, a problem though that arises in this kind of so-called off-policy learning is when you do train an epistemic neural network, you know, more often than not, when you look at the results and you'll say, gosh, what have I learned, and how can I use that to improve on the previous policy? You know, usually the answer is, you know, you've learned a fair amount about that policy, and you can probably improve a little bit, but not much, based on what you know so far. Right? And that's a fundamental issue in off-policy learning. There's a lot of power in being able to probe an environment and actively learn more. So for example, in science, right? That's the difference between being able to run experiments to learn about the universe versus just observing and just trying to draw inferences from passive observation. Right? There's a big difference to the rate of progress in science that is due to the ability to do experimentation.
Thanks a lot.
Now, you showed us an example in one dimension. If we tried an epistemic neural network on the Mujoko problems, I don't know if the Mujoko problems are good ones, but what would it do?
So Mujoko has the opposite problem. Mujoko's problems are designed to look fancy, but to be really easy. So any agent does pretty much, right? So this cart pole problem, it's not really one-dimensional because there's physics to this, momentum and all that. This cart pole problem is designed to look really simple, but be hard for agents. So it's sort of the opposite end of the spectrum. Right? So Ben Brecht has a nice paper on this where he sort of applies the most trivial agent one can imagine to Mujoko, and it does very well.
He does a linear quadratic.
No. I think he does this like just very random search.
Oh, okay.
So Ben, you touched on maybe something that would help me get an intuition here, which is the physics of the situation, because I was trying to think about like what kind of summaries, you know, as you were talking along about producing kind of sort of summary models or of the state of the system. You know, I can imagine that the system just understands sort of position of the you know, that its representation of the state is like the position or the angle of the stick or something like that. But a more complicated representation is the energy in the stick, you know, which has a lot of history built into that already. And I guess I'm wondering, does this system, once it learns this stuff, does it have something when you look inside of it that looks like the energy that's in the stick or something like that?
Not that I can see, but I think you raise a really interesting point. Right? If you have an agent, one of the benefits of having a automated agent is, you know, you can apply it across many things at once and gather all this data, much like what's going on with 100 workers working this cart pole, but they could be doing different things, right? And it seems that, you know, an important part of the future of reinforcement learning is to make sure these agents can generalize in a way where they learn, physical laws that are common to all these environments that they're operating in. So I think that's a really important thing. But this particular agent that I'm applying here, I don't think is intelligent about that.
Thank you. Thank you.
Go ahead.
Okay, I have a couple of questions. The first is, let's say you mentioned our target is to minimize regrets. But what if we consider a situation that we have two phases? The first phase, we don't care about regret. We only want to learn the Q value as best as possible. In the second phase, we want to implement. Let's say we give it our algorithm to the client to do its best performance. So that in the first case, we can still do sequential update, right? But in that case, is our information, I remember there's a formula there. We have an information metric, right? That would be different.
Yeah, so that would be a different objective. And typically, these days reinforcement learning agents are not designed with that objective in mind. But usually you can take them and tinker with them to do something reasonable with that objective.
Okay, the second is for the ENN network just mentioned, I'm a little bit curious. You add a reference distribution, let's say normal 0, 1, right? Is this something? What's the intuition there? Is it like something similar to GAN, or you want to predict a distribution, or can you give more detail on that?
Yeah, so it's a way of representing, for example, a posterior distribution over neural networks, right? So the idea is, it's a representation where you're not explicitly representing a posterior distribution, but you're representing it in terms of something that can sample from that posterior distribution, right? And so you can think of Z as, perhaps a seed that you feed in to sample one neural network from that distribution.
So that means in practice, when we use it, when we have a state, and each time we sample from normal, we will have a different prediction, right?
Correct.
Okay.
And so if you wanted the variance of your prediction, for example, you could plug in a bunch of different values of Z sampled from this normal, and then look at what the outputs are for each one, and then compute a variance, for example.
Okay, so in that case, let's say in practice, usually we select the A that maximize the QSA, right? But in that case, what might be the metric we select the action?
So one possibility is this information ratio, right?
Okay.
So the numerator is sort of like optimizing the expectation of QSA, but the denominator is of the information ratio is measuring how much information you're going to gain as a consequence of that action.
I see. Okay. The third question is, the most example you mentioned here is more like those games, or let's say AlphaGo, we have a clear loss function that is win the game or whatever, or get some score. In some practical implementation, let's say the loss function is not easy to get, or let's say autonomous driving, or maybe self-cooking machine. Do you think let's say for our DQN, you have a comment how to, from academic perspective, we can design good loss function?
By loss function, do you mean like a reward function?
Yes, reward function.
I don't see that as part of the reinforcement learning problem. And actually, there is a cottage industry in reinforcement learning, people working in it, but I'm not a fan of that. So I think of the reward function as an articulation of preferences, right? Of subjective preferences, right? But there's a subfield of reinforcement learning that tries to design the reward function to get the agent to do what they want the agent to do, right? And that, I think, tends to conflate the general design of an agent with how to solve a particular task, right? So I think that's something to be careful for if you want to design an agent that you can plug into many different things.
Okay, thank you.
All right. Well, thank you very much, Ben, for a really excellent talk. It's a pleasure to see you here, and we wish you lots of success with these really difficult problems.
Thank you very much. And it was fun to be with you.
Right. Goodbye. Goodbye, everybody. Thanks for coming.